Okay, this is our fifth video on the work energy theorem in our work and energy module. In this video, we're going to be focusing on non-conservative forces, and so let's jump right into it here. So forces can be either conservative or non-conservative. For now, there's no other option for us. Okay, so either a force is conservative or it's non-conservative. Non-conservative forces are path dependent. Okay, so we can think of things like friction. We can imagine that, like we spoke about before, for the gravitational force, we have this path independence, right? It doesn't really matter how we get across this distance h here, but in the end, we're going to have the same gravitational potential energy because both of our h's are the same here. For friction, maybe it's easier to think about dragging. Well, let's say we had, for example, some sort of an inclined plane, and we had to drag an object up this inclined plane, right? So let's say there was some friction here. This was some kind of rough surface or something. Then at the end, we will have lost some energy in the system. We'll have to have done extra work to push this thing up the ramp, and even if this is h, even if we have this same gravitational potential energy that we would have in this case, we've had to do extra work against friction to push this thing up the ramp, right? So maybe this isn't the greatest example, but basically what we want to think of when we're thinking of non-conservative forces, think about path-dependent forces. We want to think about systems where we're doing work and the work is sort of bleeding out of the system. We're not able to recover all the work. It's not all stored in the sense that we have potential energy that we can make use of, right? So because of this path dependence, there's no potential energy associated with non-conservative forces. Okay, so we don't have a potential energy associated with friction. And the work done by non-conservative forces will then either add or remove mechanical energy from or to our system, right? So we need to be thinking about adding non-conservative work to our system, and we're going to kind of see how this works as we take a look at the work energy theorem here. So this is us looking at the work energy theorem and how non-conservative forces can be included in our idea of the work energy theorem. So let's start off for the work done by non-conservative forces, WNC here, and the total work done by conservative forces. It's no surprise that we can write the net force as the work done, or the net work, I should say, as the work done by non-conservative forces plus the work done by conservative forces. It's not surprising because we have no other options. Either work is conservative or non-conservative. So clearly the total work has to be some sum of non-conservative and conservative work. But the work energy theorem tells us this basically, right, from before. But we now know that we can break up our network into non-conservative and conservative parts, right? But what we did before, when we were just in the last video, we were talking about how the work done by conservative forces is just the work or the energy that's changing from potential to kinetic energy, or vice versa, either potential to kinetic, like we're changing our say gravitational potential energy into kinetic energy. This thing is accelerating as it falls towards the ground, or vice versa, we're lifting this thing up through a gravitational field and storing potential energy in the system. So we argued how this conservative work done is really just the change in our potential energy. We argued this in the last video, and we're going to make use of it here. If we reorganize this equation here, we basically just this equation here, if we just equate, well, I guess what we're doing here really is just rearranging the stuff on the left to the right and vice versa, and then we're just going to replace our conservative work done by the change in our potential energy. And if we do that, we end up with the equation that we have down here, equation 3. And so from this point forward, we're basically just going to break things up. So we're going to break up these two deltas again, and move everything that's not non-conservative work done to the right-hand side. And so we have our delta kinetic energy and our delta potential energy here broken up. And if we reorganize these, so I mean already this is starting to look somewhat familiar, but if we reorganize these into this form here, then we see really that what we have is sort of another statement of our conservation of mechanical energy, except we are now considering the non-conservative work that we do. So energy will not necessarily be fully conserved because we're doing some, or at least we're considering the possibility of doing some non-conservative work to our system here. So let's take a look at what this equation is really telling us, and then we'll make use of the equation here with a couple of examples. So what this equation is telling us really, that we can see just by the terms here, is that the sum of our kinetic and potential initial energy, so initial kinetic and initial potential energy, plus the non-conservative work that we do to the system, has to be equal to our final kinetic energy plus our final potential energy, right? So we have some initial energy, either kinetic or potential. We do some work to the system, and then after all the work is done, we have some final kinetic and potential energy, right? And we're going to find that this equation, specifically written in this form, is a pretty powerful tool for us to answer some questions here. So let's take a look at some examples. So the first example we're going to look at is a baseball player sliding on level ground. Okay, and so I have some numbers calculated here, so we can put numbers to this. I think I have it, yeah, over here. Okay, so let's start off by just rewriting our new equation here. Okay, so what do we have? Well, we know that the kinetic energy, the initial kinetic energy, plus the initial potential energy, plus whatever non-conservative work we do, has to be equal to the kinetic energy final plus our final potential energy. And what do we have? So this baseball player slides to a stop on level ground, so we want to calculate the distance a 65 kilogram player slides given an initial speed of 6 meters per second and a force of friction opposing their motion at a constant 450 newtons, right? And so let's just start filling in what these terms might be, right? So we know that we have some initial kinetic energy because the player starts off at 6 meters per second, so we definitely have some half mv initial squared. We're going to consider the ground, the level ground that this player is sliding on, as our 0 y, right? So we can imagine that we have some coordinate system like this, x and y, and the player is just sliding on this surface, right? So there's no change in y, so there's not going to be any change in potential energy. So these are going to be 0. Potential energy initial and potential energy final will be 0. The final kinetic energy is also going to be 0. The player comes to a stop, right? So once the player is stopped, V is 0 and there is no final kinetic energy. And what is the non-conservative work being done here? Well, let's think about our definition for work. We know that work, and I'm going to call this the work done by friction, is just going to be equal to our force of friction times our displacement times the cosine of the angle between them. But again, if we go back to our sort of picture here, we can see that if our player is sliding in this direction here that I've drawn, this is going to be the direction of our D, but our friction, F, is going to be operating in the exact opposite direction. So basically we're going to end up with a theta equal to 180 degrees, and the cos of 180 degrees is just minus 1. And so this is just going to become minus FD. Okay? And so a bunch of this stuff went to 0, and we rewrote a whole bunch of it. So let's just take a moment here to reorganize things. What do we have? We have 1/2 mvi squared minus FD is equal to 0. And so we can just reorganize this. Basically what we're looking for here is D, right? We want to calculate the distance that this player slides. and that's our D. So let's isolate D here. I'm going to move the second term to the right-hand side and then divide through by F. And if we do that, we're going to find that D is equal to mv initial squared over 2F. Okay, so that's going to lead us to our answer. We know what M is, so I could substitute in numbers here, but we won't really bother doing all that. We could substitute in, or here I could rewrite it one time. So we have 65. Then we're going to have 6 squared over 2 times 450. Okay, and if we solve this, or we simplify for D, we're going to find that this player slides 2.6 meters. Okay, so that's our first application. And now, could we have solved this problem in another way? Yeah, for sure we could have, right? We could have easily applied Newton's second law, and maybe I'll just sort of sketch out how we could have done this. So we can think of the free body diagram. We know there's going to be some normal force. There's going to be some force of gravity acting on the player. The player is sliding in that direction, but there's no force in that direction, right? The only force is in the opposite direction, which is friction. So Newton's second law would tell us something like F net equals ma equals F, right? And so we could get an acceleration from this. We would end up finding that A is just equal to the force of friction over the mass of the player. And then using kinematics, we could take this acceleration and our initial velocity of 6 meters per second, use our kinematic equations, and find out what the time is when the velocity equals 0, right? And then or find what the distance is, right? Like we could easily do it using v squared equals v naught squared plus 2a x minus x naught, right? Or whatever, right? So we could just use whichever combination of our kinematic formulas we wanted to, and then solve for say in this example what x would be, and that would give us our d. But we did it a different way. We did it using these energy considerations, and that's because it sort of leads us into situations where it would be much more difficult to not use energy considerations. This is one of the real powers of using these energy type solutions. You can solve problems that maybe you could solve using forces and kinematics, but would be much more difficult. And we're going to see an example of that in our next example here. We're simply just going to take the same baseball player here, except now the baseball player is sliding up a 5-degree incline as they're sliding to a stop. Okay, so what can we imagine here? We can imagine, I'll draw it out here. It's kind of, well, maybe I'll draw it backward. So I'll draw it like this. We have an incline like this. We have some angle theta in here, and the baseball player is sliding up in that direction with some initial velocity, and they're going to come to a stop somewhere, say here, and at this point we're going to have some h, right? They're going to have gained some potential energy as they slide up this hill, and we want to solve for what this d is, right? So d is going to be this distance in here. Okay. All right. So how are we going to do this? Well, we go right back to the equation that we just wrote down a second ago. We have our kinetic energy initial plus our potential energy initial plus the non-conservative work done has to be equal to our final kinetic energy plus our final potential energy. Okay. And again, what do we have in this situation? Well, we do have some initial kinetic energy. We have a half mv initial squared, right? Initially, we have no potential energy because we're going to call this our y equals 0. Oops. Right, so we can imagine some y-axis running in this direction and some x-axis. So this would be y equals 0. And so we're going to have no potential energy initially. We just saw, and I won't go over it again, but we just saw how the work done here is going to be negative the force of friction, or the magnitude of that force of friction, times our displacement. in the end, we're not going to have any kinetic energy, right? This player is sliding to a stop. But what we will have now, which is different than what we had before, there's going to be some associated potential energy, some associated gravitational potential energy with the player, because they're going to be ending up higher up here than they were when they started to slide, right? So maybe the first thing that we want to do here is let's solve for what h is in terms of d. That'll eliminate one of the variables that we don't know. We don't know what h is, but we can solve for h in terms of d. We can easily see that h, and if we just think about that, right? Our mnemonic for remembering all the sort of trig functions. If we think about that, we can see right away that h is just going to be d sine theta, right? Okay, so if h is d sine theta, then we can kind of clean this equation up already. So let's do that right away. This is going to tell us that 1/2 mv initial squared minus fd is equal to mg d sine theta, right? And so let's be careful here. We want to keep in mind what we're trying to do here. We're trying to solve for d, and really there's not much left to do. We already know what theta is. We know what g is, we know what m is, we know what f is, we know what v initial is. So all we have to do is just solve for d and then plug in numbers and solve that last equation, right? So we can do that here. I guess we'll let me slide a few things around here and we'll solve for that. So let's say we have 1/2 mv initial squared equals, and I'm going to factor out the d here because we want to solve for d. We've moved the f over to the right hand side, so it's going to be a positive f plus mg sine theta, right? And then we're just going to want to divide through by these terms here, right? So we're going to end up with the d equals mv initial squared over, we're going to have a 2 in the basement here, f plus mg sine theta, and that's our solution in equation form. If we then substitute in numbers, and unfortunately I didn't do that here in my notes, so I won't have numbers for you, but I'll rewrite it, and you can just plug it into a calculator if you want. What did we have? We had 65 kilograms moving at 6 meters per second over 2 times 450 newtons plus, again, 65 kilograms, 9.8 for our gravity, sine 5 degrees. Okay, and if you plug all that into the calculator, I'm not sure what you would get. As I mentioned, I don't have this in front of me, but it would probably be something like, I better not guess. Okay, so just substitute that in there, and you'll see what the final answer is. Obviously, it's going to be somewhat less than what we found in this case, right? In fact, let me just very quickly do the calculation just to demonstrate that we actually do find that. Okay. All right. So we do end up finding that d is equal to 2.31 meters, and that is in fact less than the 2.6 meters that we found in the first part. And this is not surprising, again, because we're saving some of the energy that before would have been used to make us slide further. This is being saved in the form of gravitational potential energy, and so we slide less far. Okay? And so we'll leave that here for this one, and I'll see you guys in the next one.